All right, so I'm going to tell you about preconditioning. Let me just remind you what preconditioning is. We have the system AX equals B, and we're actually going to solve, in principle, what we do is we solve the system M inverse AX is equal to M inverse B. This is called left preconditioning because the preconditioner is on the left. There's right preconditioning, and the preconditioning that we have to do for things like conjugate gradient or conjugate residual, there's like a left and right. But it's still mostly left. Anyways, we'll talk about that later. This video, we're just looking at GMRes and BiCGSTAB. We're looking at GMRes and BiCGSTAB because those methods do not require that the matrix be symmetric or anything like that. Okay, so the idea is to solve this system here, and the point is that we want M inverse times A to have better spectral properties than A. So in some sense, we want M to be an approximation to A, so that M inverse is an approximation to so that M inverse is an approximation to A inverse, so M inverse A has good spectral properties. I mean, that's essentially what we're looking for here. Really, we want, anyways, so that's basically what we're looking for here. You might remember that when we first tried to apply, or we didn't even really do Richardson iteration, but I mentioned that for an unpreconditioned PDE matrix, Richardson iteration didn't really work, and so we could view Jacobi, GS, and SOR as a preconditioned version of Richardson. So now we're going to do different preconditioners. So the question is, what should I be choosing here for the matrix M? Well, again, it needs to approximate the inverse of A, or M inverse needs to approximate the inverse of A, and we need to be able to solve things like M inverse A, or we need to be able to compute things like M inverse AX. Now, typically, what's going to happen if we have M inverse AX? What we're going to do is compute AX and then solve this system here for Y. So we'll know AX, we'll know M, and then we'll solve this system. And there's various ways that we can do this. Now, the first thing that I want to tell you is that we have to be a little bit more sophisticated than literally just passing in a preconditioned system to the iterative method. And let me explain to you why that is, but also this is going to illustrate why preconditioning is so good. So I'm going to run this. Notice it takes 1,736 iterations. This is, if we run this a few times, many iterations. Anyways, so I'm going to do a preconditioned system here. So I'm going to say PA3 is going to be SPS.diags 1.0 divided by A3.diagonal. I hate when it does this. And we want to multiply this by A3. So this is A3 divided by its diagonal. Okay, and again, why are we choosing the diagonal here? Well, for the PDE matrices, they're often diagonally dominant, so the diagonal is sort of a good approximation to the matrix. And then we're going to say our precondition B3 is going to be equal to B3 divided by A3.diagonal. We're going to come down here. Okay, and what I'm going to do, I'm actually going to make this tolerance a little bit smaller because I want to illustrate something. This is not going to work out as well as we want it to. Okay, so notice that the relative error is on the order of 10 to the minus 5, but the absolute, or the absolute error between the solution and the approximate solution is only 0.5. Well, what's going on here? So the issue is that we are solving this system D inverse AX is equal to D inverse B. And so when we compute the residual that gets computed is really going to be D inverse times B minus AX. Well, this is going to be less than or equal to the norm of D inverse times the norm of the residual that we care about. Okay, so in other words, it could be the case, and often is the case, that the residual that we actually care about is somewhat big, but this might be very small, and so it makes the residual artificially small. So what we need to do then is for a precondition. Now there's two things that we can do. If we want to pass in, if you just want to pass in a preconditioned system, then we have to come over here and change the iteration. So I think before, let's see, if I had the non-preconditioned, I had something like this, and it took 1,780, and we got down to something like this. Okay, if I look at a preconditioned version of this, with now instead of 10 to the minus 4, 10 to the minus 10, look, we get something close to what we had before. Actually, this is even better than what we had before, and the iterations are 100. So this shows two things. Even preconditioning with just a diagonal makes this go 10 times faster. I mean, this is 10 to 20 times fewer iterations. But the other thing that it tells us is that we have to be careful with the tolerance, because the relative residual tolerance could be something that we want it to be, but because of this relationship right here, the overall tolerance could still be large. So therefore, what we really want to do is we want to let the algorithm handle the preconditioning. And as writers of the algorithm, we're just going to have to keep in mind that when we compute residuals, we need to compute the actual residual and not the preconditioned residual. So here's how this is going to change. So we're going to come up to our BiCGSTAB algorithm. You'll notice here that I did AP is equal to A times P and AR is equal to A times R. I mentioned that in the previous video. I changed it here because it's going to be important. So now what we're going to do, I'm going to come over here and I'm going to add a preconditioner. So I'm going to show you two different ways we can do this preconditioner. First, the user is just going to pass in the M matrix. So in other words, the system that we're solving is M inverse AX is equal to M inverse B. And so essentially, in principle, what we're going to do is just apply the BiCGSTAB algorithm to this system. But we don't actually want to literally compute M inverse. So we're going to do something a little bit different. The first thing that we need to do is take care of what happens if there is no preconditioner. If this is none, now we need to have a sparse matrix. So it's going to be SPS.identity. And then we want A.shape 0. Oops. And we want it to be CSR. I think that's what it is by default. But anyways. Okay, so there's several considerations that we have to make here. Now, the right hand side is M inverse B. Now, I like to use the matrix, the letter P, to denote the inverse. So this is going to be like PB, P times B, and I'm just going to call that PB. So PB is going to be P times B, which is M inverse B. So why does that matter? Well, again, I'm applying BiCGSTAB to this system. So what I'm going to do is I'm going to say PB is equal to SPS dot linalg.triangular solve. SP solve triangular, and I'm going to solve the system MB. MX or MPB is equal to B. And what we're going to do, we're going to make a very strong assumption here, and we'll see later how we can remove this. But we're going to assume that M is a lower triangular matrix. Okay, so that this is not the best way to do it. We'll see what happens in a moment when it's not a lower triangular matrix. But for now, we're just going to do this under the assumption that we have a lower triangular matrix. Now let's come down here. Now x0 is equal to the 0 vector, which means what we have down here, this is going to be the 0 vector. And we could change this as well. Like this, the AX naught that we're computing is really M inverse AX naught. And so we could compute a P X naught as well. But since I'm doing X naught is equal to 0, just for the sake of this lab, I'm just going to take it equal to 0. Okay, and so R naught is going to be equal to PB. Okay, because again, we're solving M inverse AX is equal to PB. So in the solving of the system, we need to use PAX or M inverse AX, or whenever we see an A computation, it really needs to be M inverse times PAX, or something equivalent to that at least. However, when we compute the residuals to determine whether or not we have ended, we need to compute the residuals using the actual system b minus ax, not pb minus pax. So you have to keep both things. So r naught is going to be pb, but b norm is going to be the ln-alg dot norm. Because when we actually compute the relative residual, we need the norm of b naught, not the norm of m inverse. Sorry, we need the norm of b or r naught, not the p version of that. Okay, so now this norm here, r naught, that should be equal to b minus ax naught, but that's just ax naught is equal to 0, so I'm just going to keep it like this. Okay, again, this right here is just a line just to make sure that 0 vector is in the solution, essentially. It's kind of silly, but we need it. Okay, so I guess that means it's not silly, but it's just an irritating thing to have to deal with. And I guess I'm whiny. All right, so now if we come down here, now whenever we have a matrix computation with A, this is not AP, this is M inverse AP. So here I've got AP is equal to A times P. So what I really need to have is something like this solved. I need to have this solved. Okay. But now my right-hand side is going to be AP, and I'm going to have M here. Okay, and similarly, I'm going to have this. My right-hand side is going to be AR. Okay, and now all of the matrix computations, like this AR then, is not really AR, it's M inverse times AR. At least in principle, that's what's happening here. Okay, now for the residual. Oh, so there's another problem as well that I didn't realize when I was making this video the last time. This B needs to be beta. The reason that it needs to be beta instead of B is because B is the right-hand side, and I've overwritten it here. So now I'm going to say true residual is going to be equal to np.linalg.norm b minus ax. Yeah, that's what we want here. Okay, now if true resid is less than target, this is what we're going to return. Okay, so I'm going to do this. Now, when I run this again, everything, it should be, nothing should change because I haven't passed in a preconditioner. And so the identity matrix will be the preconditioner, which is just not a preconditioner. So if I run this, we'll at least get to see where I've made errors. Okay, looks like I didn't make any errors, which is surprising to me. Okay, so now I'm going to say my preconditioner is going to be equal to this matrix here. Okay. And down here I'm going to say M is equal to M. Okay, so now I have a preconditioner. And since I'm computing the residual, the actual residual, I'm going to actually make this back to 10 to the minus 4, and we're going to see what happens. Okay, problems. Why is this happening? Okay, so there are a couple problems. One not so big and one big. So remember that the preconditioner M, the preconditioner M is the approximation to A. So I don't need to divide by 1 here. I don't need to divide by the diagonal. And the other thing that I need to do, one of the things is format this as a CSR matrix. The other big problem is up here. I did have A at P, but it just needs to be AP like this. Okay. So now, if I run this, and then let's see, come down here, maybe make that 8. Okay, so I'm going to run it. There we go. If I make it 10, there we go. And notice that, okay, it's taking 108 iterations to run. Whereas if I don't do the preconditioner, it's going to take thousands of iterations to run. Okay, 1,773 iterations to run. Okay, now clearly we don't want to have a situation. We don't want to have a situation where the algorithm requires that the matrix, that the preconditioner be lower triangular. What if it's upper triangular? Okay, now maybe you could do something where your algorithm, you pass in a preconditioner and it says, okay, well, you have to tell me it either has to be lower triangular, upper triangular, or diagonal. But that's not really good either, because there's preconditioners that are none of those, right? Like a what if you could get a tridiagonal preconditioner? That's something that would be good. That is something that would be good as well. So we need to do something then a little bit differently here. Actually, maybe before we do that, let's see. I want to do one more. I'm going to look at one more preconditioner. So I want to look at the SPS dot lower triangular. I'm going to get the lower triangular part of A. Okay. So this is kind of like the this is kind of like this is like the what is it, a Gauss-Seidel preconditioner with Gauss-Seidel. Okay. Oh, I didn't put the precondition here. Oh, A3. There we go. And now notice we're only taking 70 iterations. Before, you're taking 100 or so. Now we're doing in the 70s. So okay, so preconditioning with the lower triangular gives us something even better. Okay, but now the idea is, what if we don't want to look at a lower triangular? What if we want to look at an upper triangular? Okay, so I don't know. I think it's like that. What if we want to look at an upper triangular? Okay, well, how we now are to the point where we realize we need to have a better preconditioned algorithm. All right, so now what we're going to do, I'm going to come up here. For BiCGSTAB, the preconditioner is going to be M inverse. The preconditioner is actually going to be M inverse, but it's going to be it's going to be M inverse in a very specific way. So it's going to use something called a linear operator that SciPy has. We're going to forget what that means for now, but we're just going to note that in the algorithm here, the preconditioner is just going to be P times whatever. So everything's going to be a lot easier. So whenever we do A times X, so here I guess what I'm saying is we're applying the system, we're applying the BiCGSTAB method to PAX equals PB. Okay, so now PB is going to be equal to P times B. And now all of this stuff is going to stay the same because we still need to compute the actual residual. But now when we come down here, AP is going to be P at A at P, and AR is going to be P at A at R, like that. Okay, so I'm just going to come down here. I'm going to run this without a preconditioner just to make sure that I haven't completely screwed it up. Okay, this looks right. And now I need to figure out what my preconditioner is going to be. Okay, so I'm going to actually make this go back to diagonal, or M is equal to SPS dot diags A dot okay, so that's what M is. So I'm going to just comment this out. So okay, diagonal preconditioner. Now, what is P going to be? So now we're going to do this thing that's called a linear operator that SciPy has. So I'm going to first make a function. So make a function. Sorry. apply. I'm using different. If you're wondering why I'm getting a little bit tripped up, I'm using slightly different notation in this lab video than I did in what I have prepared. So okay, apply. Let me do it like this. Apply an inverse on a matrix or on a vector v, and then what this is going to do is we're going to so here so we are the caller of the function, and we are assuming that our matrix M is going to be at least lower triangular. So I'm going to do SPS dot linalg dot sp solve triangular, and it is a lower triangular matrix. Okay, so that's what we're going to do. And now we're going to make a linear operator. So I'm going to call it P. P is going to be equal to the linear operator. The linear operator is under SBS sparse dot linalg dot linear operator. Okay, and the shape of this linear operator is going to be the shape of A3. Hold on. Yes, okay. And then the matvec is going to be this, and then the data type, this is probably not completely necessary, but we're going to have this. Okay, so now what this is, so P is a linear operator, and the thing that it does, if you do P times X, this is going to compute P inverse of X. Okay, so that's exactly what's going to happen here. Right now, M is a diagonal matrix, so that is in particular a lower diagonal matrix, so all of this will work here. And we're going to do P is equal to P. Run this, lin gouge, that is not right. Okay. All right. Wait, what's the... Oh, this is A3. Okay. Oh, sorry. When I do this composition up here, wait, in BiCGSTAB, when I do these compositions right here, yeah, I need to do, A needs to be a linear operator as well. So, AOP is going to be equal to SPS dot linalg dot as linear operator A. Okay, so now down here, wherever I see an A, I need to do AOP here, and then AOP here. Okay. So now this should work. All right, and we can see that it does work. 97 iterations. That's consistent with what we saw before. This is because, let's see, where am I? Oh, let's see. Oh, let me come up here. Sorry. That's what that warning is for. Okay, there we go. And again, this is we are preconditioning with the diagonal, and this is consistent with what we had before. If I come up here and instead of having m be equal to the if I have m, instead of m being equal to the diagonal, if I have it be equal to the lower triangular matrix, I'm gonna have something similar, 72 iterations. But now notice what I can do. If I want to make m be the upper triangular part, I can come down here, lower equals false, and so now we'll get something like this as well. So I can solve if I want to use the upper triangular part as well. And there's, I could use the tri-diagonal part or something if I wanted to. Anyways, so this is how we can use preconditioning. This is how we can use preconditioning for the conjugate, or for the BiCGSTAB algorithm. And you can see the videos that I did previously for the GMRes algorithm to see how we could do preconditioning there. There I was explicitly solving systems of equations, and I will let you look at that because I need to, this lab video has gone on long enough. Okay, so there we have it. This is a little bit about preconditioning. When the system that we're looking at doesn't have to, when we're using a method where it doesn't require that the matrix be symmetric or anything like that, then preconditioning, we're just going to do it like this. In the next video, I'm going to show you how we have to precondition the conjugate gradient method, because it's a little bit different. Because for conjugate gradient, we do need to have a symmetric positive definite matrix.